Lesson 28. Determining the needed amount of solution to perform a reaction. The objectives for Lesson 28 are to learn the skills necessary to determine how many milliliters of a solution it will take to make a desired amount of product. In Lesson 27, you learned how to take a known amount of solution of a known molarity and place it into a chemical reaction in order to predict the quantity of a product from the reaction. You learn that you first have to convert the milliliters of solution to grams of solute and then ultimately moles of solute before you could continue with the stoichiometry calculations. In this lesson, you will learn how to determine the amount of known molarity solution necessary in order to produce a desired amount of product. This procedure is very similar to determining the amount of reactant necessary to produce a desired amount of product that we did in Lesson 25. However, in this case, instead of determining the amount of dry reactant needed, you will be asked how many milliliters of known molarity solution it will take to make the desired amount of product. Let's begin by looking at an example. Suppose you've been asked to prepare 100 grams of potassium chloride for your boss. You found in your storeroom that you have a 5 molar potassium chlorate solution, which will readily decompose to produce potassium chloride and oxygen gas. How many milliliters of this 5 molar potassium chlorate solution will it take to make the 100 grams of potassium chloride? Let's start by writing and balancing the chemical reaction. We've got potassium chlorate, which would be K1ClO3 taken one time. It decomposes, so we'll draw the arrow into potassium chloride. Now this is the stuff we want to make. The potassium chloride, which would be the KCl plus oxygen gas. And recall that oxygen gas is diatomic, so we'll write it as O2. Let's balance the reaction now. Note that we'll insert a 2 in front of the potassium chlorate, a 2 in front of the potassium chloride on the product side, and then a 3 in front of the oxygen on the product side. Let's identify the reactions that we're interested in this reaction. We'll put a box around the potassium chlorate and then a box around the potassium chloride. This helps us determine the mole ratio, which is 2 to 2, which can be reduced to 1 to 1. Let's look back at our problem. It says, how many grams of potassium chloride are we supposed to make? Let's see. If we look at the problem, it says we need to make 100 grams of potassium chloride. Recall from Lesson 22 that we can only apply the mole ratio to moles of product or reactant. Right now, we are looking at needing 100 grams of potassium chloride, so we'll need to convert this 100 grams of potassium chloride into moles of potassium chloride. And since you've done this so many times before, you know you're going to need a formula weight or molar mass for the potassium chloride. If we do our calculations, we'll find that 1 mole of potassium chloride weighs 74 grams. Now, we've been asked to make 100 grams of potassium chloride for this reaction. Knowing 1 mole of potassium chloride has a mass of 74 grams, this allows us to create an equivalent set of fractions. We can say 1 mole of KCl is to 74 grams as X moles is to 100 grams. If we cross multiply and solve for X, we see that we need to actually produce 1.35 moles of potassium chloride. Since we have this amount now in moles, we can apply the mole ratio that we found earlier, which was 1 to 1. So based upon this ratio, we know in order to produce 1.35 moles of potassium chloride, it's going to take 1.35 moles of potassium chlorate. Now check back to our problem. We are being asked to determine how many milliliters of a 5 molar potassium chlorate solution are necessary to make this 100 grams of potassium chloride. If our available solution is 5 molar, that means there are 5 moles of potassium chlorate in every 1,000 milliliters of solution. Knowing that, we can set up these two equivalent fractions. We can say in 1,000 milliliters of solution, there are 5 moles of potassium chlorate, which is equal to X milliliters in the 1.35 moles of potassium chlorate. Or we can say 1,000 milliliters over 5 moles as how many milliliters in the 1.35 moles. Cross multiplying and solving for X, we find that the result will be 270 milliliters of potassium chlorate. Therefore, based upon these calculations, we can say that in order to prepare 100 grams of potassium chloride, we would need at least 270 milliliters of a 5 molar potassium chlorate solution. Let's look at another example. If bromine gas, so bromine gas is Br2, is bubbled through a solution of potassium iodide, potassium bromide and iodine crystals are produced. Suppose that you've been asked to prepare 50 grams of iodine crystals, which would be I2, from this reaction. If the potassium iodide solution is 2 molar, how many milliliters of this solution would you need? Let's begin by writing and then balancing the chemical reaction. It says bromine gas is bubbled through. So we have bromine gas, we'll write down Br2, is bubbled through a solution of potassium iodide. So it's Br2 plus potassium iodide, which would be Ki. This results in potassium bromide, which would be KBr, and, so we'll write the plus sign, iodine crystals. Remember, iodine crystals are diatomic, so it'll be I2. If we balance the reaction, we see that we need to insert a coefficient of a 2 in front of the potassium iodide on the reactant side, and then another 2 in front of the potassium bromide on the product side. Let's locate the parts of the reaction that we're concerned with. We'll put boxes around the potassium iodide and then the iodine crystals. This will allow us to determine the mole ratio, which in this case is 2:1. Look back at the problem now. We're being asked to prepare 50 grams of iodine crystals. Before we can apply the mole ratio to this desired amount of product, we must first convert it to moles. To do this, we need to determine how many grams are in 1 mole of iodine crystals, also known as finding the formula weight of I2. If we do those calculations, we'll see that 1 mole of iodine crystals weighs 254 grams. Knowing this amount, we can then set up equivalent fractions to find out how many moles are equal to the 50 grams we are being asked to prepare. We can set up the fractions. 1 mole of iodine is to 254 grams as X moles are in the 50 grams. If we cross multiply and solve for X, we see that X equals 0.20 moles. Based upon these calculations, we can see that our 50 grams of iodine crystals that we're asked to make is equivalent to 0.2 moles of iodine crystals. Now that we have this amount in moles, we can apply it to the mole ratio. In order to make the desired 0.20 moles of iodine crystals, it will take twice as many moles of potassium iodide, which would be 2 times the 0.2, which would be 0.4 moles. Now, our potassium iodide that we have to put into this reaction is a 2 molar solution. We know we will need 0.4 moles, but now we need to know how many milliliters that is equivalent to. A 2 molar solution means there are 2 moles of potassium iodide in each liter, or 1,000 milliliters. Knowing this, we can set up 2 equivalent fractions. We can say in 1,000 milliliters there are 2 moles of potassium iodide, so how many mils, would be X mils, are there in the 0.40 moles that we need? We can cross multiply and solve for X and find out that we would need 200 milliliters of 2 molar potassium iodide in order to make the desired amount of 50 grams of iodine crystals. To review what we've learned in these examples, let's look here. First, we attacked the problem just like any other stoichiometry problem. We wrote and balanced the chemical reaction. We determined the mole ratio and used it to predict the amount of ingredient necessary to produce the desired amount of product. We then looked at the molarity of the given reactant solution we had available and finally determined the volume necessary to meet our needs in the reaction. Practice the skills you learned in this lesson by turning to the practice pages you'll find at the end of Lesson 28 in your student textbook.